I turned it off. I turned the recording off because I wasn't seeing, my brain wasn't working. The mistake that I made was right at this step right here. I put this to the -1/2 power, but this is still, this u is still in the denominator, so that's still du over u. I'm sorry, right? So this v thought is right because here that we're going to put a dv right here, and so then we will replace 1 over u du with dv, and then instead of ln u, we'll put v in. So this will be the integral of v to the -1/2 power dv. And then that's just a regular integration. Add 1 to the exponent, put it over it. So this is going to be, if you add 1 to this, it's to the 1/2, and then it's 2v to the 1/2 power plus c. Are y'all okay? But what was v? V is ln u. But what was u? Ln, that was the secant x tangent x. That we did originally. So that's actually a pretty tricky one because you had like a double substitution. And I don't know that it would have immediately, like, I would have had to stare at it for a while before I would have recognized. To me, the first real thing that you had to see was that your u popped back up here and you got that du over u. I thought that was really tricky with the secant x dx. Okay. Let's see if we can do another one. Let's see if we'll do any better. Let's try number 10. Number 10, we want to do the integral of -ln2 to 0 e to the negative. I bet we can do this one, no problem. Integral of -ln2 to ln3 e to the -x dx. All right. So you will remember the integral of e to the x is just e to the x, but to handle that negative in front, you're just going to put a negative because it would be 1 over -1. So this is going to be -e to the -x evaluated between -ln2 to ln3. But when you do this, this will be e to the negative ln3 minus negative e to the negative L. It's going to be a negative. So this will be positive ln2. Okay. And when you're doing this problem, this negative exponent means you can actually pull that up in front. Remember the power rule? So you can think of this as negative e to the ln of 3 to the -1. And then this will be plus e to the ln of 2. And this is going to be e to the ln undo each other. So this is going to be negative 3 to the -1, which is 1/3, plus e to the ln undo each other, and that's just going to be 2. And so then you get negative 1/3 plus 2, which is, let's see, this is 6/3, so that's going to be 5/3. Okay? All right, let's try number 12. Number 12 is antiderivative 2e to the 2x minus 1 dx. This one's pretty straightforward. If you let u equal 2x minus 1, then du is just 2 dx, which is exactly what you have right here. So you're just looking at the integral of e to the u du, which is just e to the u, or e to the 2x minus 1 plus c. That one was pretty easy. Okay.
Your conference is scheduled to end in 2 minutes.
How about number 16? We'll skip. Let's see if we can get a little faster. Number 16 is the integral of e to the square root r over the square root of r. All right. Well, if you let u equal the square root of r, then du is equal to what? This is r to the 1/2 power, right? And so then this will be 1/2 r to the negative 1/2, or 1 over the square root of r dr, which is almost what you have, except that you have this 1/2 that you need to account for. So if you solve on this side for 1 over square root of r dr, you would get 2 du is equal to 1 over the square root of r dr. So where we have 1 over the square root of r dr, we can replace that with 2 du. And we can put that 2 in front. So this is 2 times the integral of e to the u du, which is just going to be 2e to the square root of r. dr. Okay?
Your conference is now over. Goodbye.
And it doesn't really matter, but I kind of made up my own problem because now I'm looking at number 16. It had a negative there, but so it doesn't matter. But because my problem's right, but I just want to warn you of that. Okay. Number 18, when you look at it, you should see that that's going to be I don't know if you can see it very well. Number 18 is going to be a pretty straightforward u substitution, right? Can you tell me what the u substitution is going to be on 18? T to the 4th, and you'll get 4t to the 3rd, so you'll have a 1/4 out in front. Okay, what about 20? Can you tell what the substitution will be on 20? You're really going to have to handle that negative 1 over x squared probably. If you let u equal negative 1 over x squared, that's negative x to the negative 2, right? And so then the derivative of that is going to be 2x to the what? Negative 3 dx, which is exactly, there it is, right? But you've got that 2 there. So it's going to be du over 2 is equal to dx over x to the 3rd. So you will replace this with du over 2. So you'll have 1/2 the integral of e to the u du. And so you'll just get 1/2 e to the negative 1 over x squared plus c. Okay? How you feeling, Brandon?
Good.
You like it? You having fun? Okay. Just little puzzles. All right, so let's see. I think maybe they'll start to get more exciting. Number 24. That one looks exciting, doesn't it? Anybody got a plan on number 24? What could we do with that? I'll write it. down here, so I have room. So number 24. Everything's big now, hold on. Was the antiderivative of the integral from 0 to, or the integral from 0 to 11, or ln pi, and then it's 2x e to the x squared cosine e to the x squared dx. So what do you guys want your u substitution to be? Yeah, I think e to the x squared is going to be your best bet, because otherwise you're going to have cosine of e to the u, and we can't integrate that. So if we let u equal e to the x squared, then du is going to be e to the x squared times the derivative of that right there, which is 2x dx. All right, so here's my 2x dx, so that's cool. Actually, this is everything, right? So I'm good. Now, I'm going to change my limits of integration. If when x is 0, e to the 0 is 1. And when x is the square root of ln pi, this will be ln pi, which will just be e to the ln pi, which is just pi. Is that okay? Or do you need to see it? Are you okay, Brandon, or you need to see it? You got it? Okay.
Good.
All right, and so then that is the cosine of u du. The integral of the cosine is the sine from 1 to pi. And so then this will be the sine of pi minus the sine of 1. Which the sine of pi is 0. But I don't know what the sine of 1 is. So this is negative sine 1, which you could type in your calculator if you wanted. Fun? These rock. Okay. Want to try another one? Let's look back up here and see. For 26, do you guys have an idea of what you would do on 26? You're going to let u equal 1 plus c to the x? All right, and then du is going to be what? Dx. So you've got that e to the x there. Kind of messing you up, isn't it? Because it's not gonna quite work on that. So I think we're gonna have to be snazzy. I mean, I know the trick. I'm just trying to explain. I'm trying to think, how am I going to tell you about this trick? All right, for fun, I mean, this is just a trick, okay? So this is, it's just kind of like this one was a trick, number 8 was a trick, this one is also another trick. That is, number 26 is a trick. So another tricky. 1. And it's kind of a strategy, I guess, a little tool that you might use. You know, if you don't have something in your numerator that is going to help you when you make your U substitution, then you might want to try and force something in your numerator by dividing everything by the same thing. Now, a clever thing to divide everything by would be e to the x. Okay? So if I divide each term of this by e to the x, that's not illegal. Okay? So I'm going to divide this by e to the x, this by e to the x, and this by e to the x. Just a little thought. Okay? And then what's going to happen is you're going to get the integral of, well, 1 over e to the x is e to the negative x. And then here, this is going to be e to the negative x plus 1 dx. Okay? Well, that's a whole lot cooler. Oh, this is a e to the negative x also. That's a whole lot cooler to make a U substitution with, right? So, but it was kind of a trick knowing to divide everything by e to the x. But sometimes manipulating equations is a little strategy that we use. All right, so now if I let u equal e to the negative x plus 1, then du is going to be negative e to the negative x dx, which is exactly what I have in the numerator, except I've got the negative, which I can handle. So this is going to be negative antiderivative du over u. And what is the antiderivative of du over u? That's just your ln u. So then this is just going to be ln absolute value of u plus c, and u was this e to the negative x plus 1. So this is negative ln e to the negative x plus 1 plus c. And you don't actually have to have absolute values because e to the x or e to the negative x is never negative. It just looks like that. So it's not wrong to have the absolute value, but you don't need them. So that was another tricky one. I wish I had a better justification for why I divided everything by e to the x, except that I've been doing it a long time. You've seen it before? Okay. All right, so I don't know if you remember it because it doesn't come up all the time. All right, let's see if we can get tricked out again. All right, number 28, 5 to the negative theta. All right, negative 2 to 0, 5 to the negative theta, d theta. This one's actually pretty straightforward because we have a formula for working these. Negative 2 to the 0, 5 to the negative theta, d theta. This is like thinking of the integral from negative 2 to 0 of 1/5 to the theta d theta, right? And this is, by definition, or we have a theorem up here. I'll show it to you all the way up here. The integral of a to the u is a to the u ln a plus c. So our a was 1/5 here. So it's going to be 1/5 to the u ln 1/5 plus c. Or theta. Yeah. Okay, so this is going to be 1/5, instead of to the u, though, it's to the theta. So it's going to be 1/5 to the theta ln 1/5 evaluated between negative 2 and 0. And so you can kind of take this 1 over ln 1/5 out. And when you put 0 in, 1/5 to the 0 is just going to be 1. Minus 1/5 to the negative 2. All right. This is 1 over the ln of 1/5 is the ln of 1 minus the ln of 5, right? But what's the ln of 1? Yeah, so this is just 1 over negative ln 5. And then this is going to be 1 minus, what is 1/5 to the negative 2? It's an algebra question. Brandon, wake up. Are you sleeping? Are your eyes closed?
No, I was thinking about what it was. It's like,
Yeah, it's remember the negative exponent means flip it. Like if it's 5 to the negative 2, that's 1 over 5. But anyway, this since it's already flipped, you're going to flip it back. So that's 5 to the 2, which is 25. But say you're having a moment, your calculator can be real helpful. You know, like you could type it in and you'd be like, oh yeah. You know, like 2 to the negative 4 is 1/16th, right? 2 times 2, whatever 2 to the 4th is. I'm having a moment. Yeah, 1/16th. So 1/2 to the negative 4 will be 16 because you just flip it. All right. So this is negative 24 over negative ln 5, which is 24 over ln 5. Okay, are we having fun? These are so much fun. All right. Should we do 30? All right, here's 30. 30 is the integral from 1 to 4 of 2 to the square root of x over the square root of x. I think that's what it is. Yeah, 2 to the square root of x over square root of x dx. Okay, so I'm thinking, and you guys have an idea for you? Oh man, come on now. How about square root of x? So du is going to be what? Because this will be x to the 1/2 power. So this will be 1/2 x to the negative 1/2. So 1 over the square root of x dx. Does that feel okay? Which is exactly, I didn't put my dx here, but that's exactly what you have, dx over the square root of x, except for this 2, we're going to write this as 2 du equals 1 over the square root of x dx. So we'll put this in here. And so we'll put a 2 out front. And we'll have the integral, and it'll be 2 to the u du. And I'm going to go ahead and change my limits because that's always fun. When x is 1, u is the square root of 1, which is still 1. But when x is 4, u is the square root of 4, which is 2. All right. Then we learned that the integral of 2 to the u du is 2 to the u over ln 2. Because it's a to the u over ln a. That's just the formula. So this is going to be 2 to the u, oh, we got this 2 here, over ln 2 from 1 to 2. Don't be crazy and think you can do 2 times 2 here. You could do 2 to the u plus 1 if you wanted to be crazy, but I don't know how crazy you're thinking. All right, so this is 2. This ln 2 can come out also. So this is 2 over ln 2. When I plug a 2 in here, I'm going to get 2 squared minus 2 to the 1. So this is 2 to the 4th. 2 squared, which is 4, minus 2. So it's 2, so it's 4 over ln 2. Should be your answer. All right? Pretty fun. Let's see what else we got going on here. 32. Isn't this like crazy? I didn't even talk about it, but what we're looking at here are what we call transcendental functions, meaning these functions are just so non-algebraic. Transcendental is non-algebraic. They're so weird. Like 1/3 to the tangent t secant squared t. I mean, just as a function, that is so weird. Don't you think? It's very transcendental. It's not like x squared plus 5x plus 7. You know, it's really, I have no idea what the graph of that function looks like. All right, so 1/3 to the tangent t secant squared t dt. That, hopefully you're thinking that's not going to be too bad because the u sub could be what? Yeah, if you let u equal tangent t, then du, the derivative of the tangent, is secant squared. So you're going to have 1/3 to the u pretty fast. All right, so let me come down and do that one. I forgot, is that 32? Is it 32? Yeah. So it's the integral from 0 to pi over 4, the 1/3 to the tangent of t secant squared t dt. So if you let u equal the tangent of t, du is secant squared t dt. So you're good to go right there. You've got exactly what you need to replace. I'm going to go ahead and change my limits of integration. The tangent of 0 is 0 because that's sine 0 over cosine 0, which is 0 over 1. So it's 0. The tangent of pi over 4 is 1. So this is the integral from 0 to 1 of 1/3 to the u du. We just learned the formula for the integral of this, a to the u, is a to the u over ln a. So this is going to be 1/3 to the u over ln 1/3 evaluated between 0 and 1. Now, you can put that ln 1/3 on the outside like that. And this is 1/3 to the 1 minus 1/3 to the 0. Which is, now what did I say about ln 1/3? What's that the same as? You can use, yeah, ln 1 minus ln 3, but the ln of 1 is 0. So that's really just negative ln 3 equals, times 1/3 minus 1, which is negative 2/3. So this is going to be, and then we have that negative there, so it'll cancel out. So this will be positive 2 over 3 ln 3. Is this fun? No. Awesome. All right, so let's look back up and see if we can find any more that just look like they would be totally fun to work. 34 looks pretty fun. What do you want your u to be on 34? Brandon, can you see it?
Samuel Sanchez,
LNX.
80 Bates, comes office.
How about just ln x?
Ah.
That's a good idea, don't you think? If you do too much for your u, then your derivative gets really messy. Like the derivative of 2 to the ln x is going to have a lot of stuff in it, you know. So probably don't want to do too much. Because then what happens here is this is 1 over x dx, which, hello, that's exactly what you wanted, right? Because there it is, 1 over x dx. So this is going to be 2 to the u du. Now, this will go ln 1 to ln 2. So this will be from, ln 1 is 0, so this will be from 0 to ln 2. So this will be the integral from 0 to ln 2, 2 to the u du. And this is 2 to the u over ln 2, evaluated from 0 to ln 2, which is really weird. But anyway, it's 2 to the ln 2. It's 1 over ln 2. 1 over ln 2. And then this is 2 to the ln 2 minus 1. Which you really can't clean that any more than that. If it were e to the ln2, that would be 2. But 2 to the ln2 is just what it is. Okay. 36, like they threw that bad boy in there just to mess with your mind. All right? But 36 is just an add 1 to your exponent and put it over it. Because that's just x to a number. Do you see what I'm saying? Like x to the 5th dx. But it's x to the ln2 minus 1. So you're just going to add 1 to the exponent and put it over it on that one. Which is going to be, when you add 1 to this, you're just going to get ln2. So this is going to be x over ln2 to the ln2 evaluated from 1 to e. Which is going to be e 1 over ln2. You can put that in front. That's e to the ln2, which is just 2, minus 1 to the ln2. So that's for the...
Make sure you get the right. Well, you did. You just added 1 to the exponent and divided that whole thing by 1.
Right. Like if this were x to the 5th, you would just go x to the 6th divided by 6. Right? You would add 1 to the exponent, put it over it. So my exponent is ln2 minus 1. If I add 1 to ln2 minus 1, I get ln2, which is just what I put over it. So that's where I got that's what I put it over, and then it's x to the ln2. So it's like they just threw that one in there just to mess with you. I could have asked you that when I first showed you how to integrate. Add 1 to the exponent, put it over it. All right. Are we having fun? All right. Now, a problem like number 38, when we're dealing, when you're dealing in a different, let's see, do they give us a formula for the antiderivative in a different base? I think they did. Or do they? I can't remember. The integral of log base A. Did they give it? Is it in here? I don't think they actually do. They give the integral of a to the u, but they don't. Yeah. I don't, if I was doing, do you guys remember the change of base formula? Yeah, Miss Brooks, we just remember all this stuff. The log base b of a is equal to the ln of a divided by the ln of b. Okay, that's the change of it. Because that, on your calculator, you only have log and ln. And so if you wanted to do log, and I'll give you one that you know, maybe log base 2 of 8, that means 2 to what power is 8? So you should know the answer is 3. But on your calculator, you can't do that without, there's no log base 2 on your calculator. But what you can do is you can do ln of 8 divided by the ln of 2. So you do the log of the number divided by the log of the base, and that'll give you the 3. That's called the change of base formula. It turns out you could actually have used the LOG button if you preferred, as long as you're consistent. You have to use the same one. You'll still get 3. You can you can go from one base to the other with this change of base formula. So when you see it if you Googled it, it may not put the ln's here. It might just say log some new base c of a over that same new base with the b. okay? But it makes sense to use the ln because that's the one we know the integral of, and also because that one's on our calculator. Okay, so back to problem number 38. Log base 2 of x over x dx. The antiderivative, or the integral from 1 to 4 of log base 2 of x over x dx. All right, so let's go ahead and use the change of base formula on log base 2 of x. So this is going to be the integral from 1 to 4. This will be the ln of x over the ln of 2. So we can write this as the ln of x over the ln of 2 divided by x dx, which we can write this, this is from 1 to 4. You can put this ln 2 and this x. They can live together in the denominator. So this is ln x over x ln 2 dx. And of course, ln 2 is just a number, so it can come out in front. So this is 1 over ln 2, antiderivative 1 to 4, ln x over x dx. Now, how do I integrate that? Yes, let u equal, yes, ln x. And then du is 1 over x dx, which is exactly what you have, right? So this is just, and you can change your limits too, which will be fun, I guess. 1 over ln 2, the integral of, and this will go, when x is 1, you will be ln 1 to ln 4, and then this was just u du, which you just add 1 to the exponent and put it over it. So this is going to be 1 over ln 2, u squared over 2, evaluated from ln 1 to ln 4. All right, now we get to be really cool algebraists here. 1 over, I'm going to bring this 2 in front, so 2 ln 2. All right, ln 4 squared minus the ln of 1 squared. Now, of course, the ln of 1 is 0, so this just falls out, right? I wonder how I want to think of this. Okay, you have to be pretty snazzy here. 1 over 2 ln 2. This is ln 4. But do you guys agree that ln 4 can be thought of as ln 2 squared? Right? Yeah? And then this 2 can come in front based on the power rule. Yeah? Okay, so this is going to be 1 over 2 ln 2 times 2 ln 2 squared. Well, I've got 1 down here and 2 up there, so the final answer is just what? So, see, I have 2 ln 2 times 2 ln 2 over 2 ln 2. Because this is 2 ln 2 squared means 2 ln 2 times 2 ln 2, right? So don't you agree that I can cancel this with one of these?
Oh.
And I just get 2 ln 2. But what is another way to write 2 ln 2? Well, you could use the power rule and bring this back up here, and you could write it as the ln of 2 squared, which is the ln of 4. So cute. So cute. I don't know how picky the online homework's going to be. I mean, I would probably be happy at 2 ln 2, but if it... Pardon?
It's called me out on
Not simplifying. Yeah, I don't know whether it will call you out on that or not. So you want to think about that. So that was fun. All right, that was number 38. I'm going to go into the initial value problems now because we just have a few minutes left. So these initial value problems, these are differential equations. Basically, they're just integration problems, but they give you a initial value or a starting value. So if we look at a problem like number 48, we could get busy on this. So let's see. This is just integration. I'll show you. All right, so 48 was, what was it? Maybe I can get it from here. Probably should have typed these out. dy dt equals e to the negative t secant squared pi e to the negative t. And we know that y of ln 4 equals 2 over pi. Okay, so this is the information that you're going to use to find your constant, to find your c. So they want initial value problems. They tell you what the derivative is. They want the original problem. That's a differential equation. So they want the y. They tell you the derivative. They want the y. So naturally, you're just going to integrate this. Y will be the integral from e to the negative t secant squared pi e to the negative t dt. But you're going to have a plus c. Then you're going to use this information to figure out what your c is. Okay? So what should your u be on this one? Your u should be this pi e to the negative t. So then your du is negative pi e to the negative t dt, which is pretty much what you have there. There's your e to the negative t. You just need a negative 1 over pi in the front. So this is going to be equal to the integral of negative 1 over pi secant squared u du. What is the antiderivative of secant squared? Tangent. So this is negative 1 over pi tangent u plus c, where u was pi e to the negative t. So this is negative 1 over pi tangent pi e to the negative t plus c. Okay? But we were given, that's what y is. We know that y, when t is ln 4, is equal to 2 over pi. So we will plug ln 4 in for t, and we'll plug 2 over pi in for what? For y. And then we'll solve for c. So we will do 2 over pi is equal to negative 1 over pi tangent pi e to the negative ln 4 plus c. And this is kind of fun. I mean, there's lots of ways to simplify this. If you're going to multiply by the reciprocal here, right? So the pi's are going to cancel. Wait, never mind. Just kidding. I was being funny. All right, so this is 2 over pi equals negative 1 over pi. All right, this negative can come up in front here. And that's going to be ln 1/4, or ln 4 to the negative 1, which is, and then e to the ln, those cancel, so this is just 1/4. So this is the tangent of pi over 4 plus c. Everybody okay with that? Because e to the negative ln 4 is just 1/4. because the negative goes up, that's 4 to the negative 1 power, which is 1/4, and e to the ln undo each other. So you just get 1/4, and then times the pi is pi over 4. The tangent of pi over 4 is 1, so this is negative 1 over pi plus c, and then we add 1 over pi to both sides, and we get 3 over pi is equal to c. And so the answer to the initial value problem is this plus c. So negative 1 over pi, tangent pi e to the negative 2, e to the negative t, plus c, which is 3 over pi. So you use the given information to find your c. You're just going to integrate, and then you have a plus c, and then you plug in your given information to find the c. So that's how you do those initial value questions. So today's lesson was just a bunch of integration tricks. So hope you have fun with that.